Welcome everybody, my name is Rodrigo Cifuentes Lobos, and today I'm going to briefly discuss and describe my master's thesis titled Implementation of a Numerical Methodology for the Stochastic Characterization of the Valdivia 1960 9.5 moment magnitude tsunami source. This research is done under the guidance of Ignacia Calisto. As a short introduction, we will be using numerical tools from probabilistic tsunami hazard assessment, such as the logic tree, to create random tsunami source models in the form of slip distributions from the combination of fault parameters such as rupture limits, aspect ratio, etc., and mathematical modeling such as the Karunen-Loew expansion. And these models are then restricted using paleo or historical tsunami data in order to discard those that do not comply with the data. Finally, a statistical analysis is performed on the remaining models in order to assess the most likely source model according to the data available. The 1960 Valdivia earthquake is used as a benchmark test. The hypothesis proposed is that the estimation of the most probable source model of the Valdivia 1960 tsunami, namely the slip distribution on the rupture geometry and rupture limits, obtained via analysis of random tsunami source models generated using a logic tree structure approach, will allow us to achieve a solution that converges to and satisfies the available paleo tsunami data, geodetic and mareograph-derived data. We propose also two research questions that is it possible to characterize the source of a historical tsunami, such as the Valdivia 1960, in the Chilean margin based on restrictions given by paleo or historical tsunami records? And does a logic tree structure approach to generating random tsunami source models allows to converge to the source model of a historical tsunami? The methodology that we use is that to generate random slip models, we combine fault-defining parameters using a logic tree structure, as shown in the figure in the left. With this combination of parameters, we use a truncated Karunen-Loew expansion, as proposed in Levesque et al. 2016, for the generation of random slip models. These models are then filtered in a staggered fashion, with filters increasing in complexity in each step. We use deformation and tsunami data from the Valdivia earthquake to assess the compliance of these models to the observations, discarding those that do not satisfy them. Those models that pass every filter are then analyzed and compared with the known Valdivia 1960 models to validate our results. This whole process is summarized in the figure on the right. As data, we have two main groups. One is deformation data, which contains uplift data, subsidence data, and the places that do not show any changes, and tsunami data regarding wave arrival data, inundation height, and run-up data. In the figure on the right, we have a map showing the locations where we have this data availability. The analysis that we will be performing after all the restrictions, that every model that passes these restrictions will be subject to statistical analysis in order to assess their convergence to the known Valdivian 1960 models. And the figure on the right shows a simplified schematic of the workflow that we will be following. These are the preliminary results showing an example of random slip distribution on the left, generated via the logic tree approach, and its corresponding vertical deformation field on the right, computed with the Okada 1985 solution. This is an example of a model that passed empirical relations and the deformation data filter, and the data filters using tsunami data is still to be performed. Thank you for your attention.